Okay, so welcome everyone to the first meeting of this new year, and I'm sorry, apologizing for this inconvenience about shifting to the new link. So our speaker today is Shalmoli, and she's going to talk about the radio polarimetry with the UGMRT, and Preeti might join us also in the meeting. So over to you, Shalmoli.
Yeah, so Preeti will be joining shortly, but till then I can continue. Uh, Hello everyone. I'm Salmoli Ghosh from National Center for Radio Astrophysics, DIAFA, Pune. And as Janki mentioned, I'll be talking about the work that we are doing with the polarimetric data from the most sensitive radio telescope in the world at such low frequencies called the Giant Meter Wave Radio Telescope, or the GMRT. This U is for the upgraded version of it. We study the radio lobes of that are emanated from this supermassive, highly energetic black holes called the active galactic nuclei, and we basically study the radio polarization from the synchrotron emission. These are some of our results from the last 3 years, which we obtained from the polarization sensitive data from GMRT band 4, which is centered at 650 megahertz. Now the thing is, with GMRT, we get both advantages and disadvantages for polarization studies. So the mm, best benefit that we get is we detect polarization even in the diffuse lobes of this region. Um, and as you can see over here, there are like a lot of diffuse emission has been picked up, and polarization is also detected in them. So the issue with other telescopes working at high frequencies is basically these lobes are very steep spectrum, and due to that reason, at higher frequencies their flux densities are low, and it's not picked up by other high frequency telescopes. So GMRT is kind of gives a plus point in that factor. But the issue with polarization at such low frequencies is that we get affected by some term which we call as rotation measure. Uh, but I'll come to that. But let me first explain what this image means. These are basically the synchrotron plasma shown in color, and the sticks are the polarization vectors with their magnitudes kind of proportional to the polarization fraction or the polarization intensity, and their angles are basically the polarization position angles or the electric vector position angles, which we call as EVPS. Now this position angle which we observe um, is not the intrinsic position angle. So the difference between the two is estimated with the term Rm, which is rotation measure, times lambda square, where lambda is the wavelength. So basically, when we go to the high wavelength regime or the low frequency regime, this term becomes huge, and that's why the observed polarization angle is like deflected by large angle error from the intrinsic polarization angle. Now, if that angle is quite a lot, then it suffers sometimes depolarization and affects the polarization fraction as well. Um, Also, like if we go to lower frequencies, we have to also keep this in mind that the beam becomes larger, which introduces some certain other stuffs like beam depolarization and yeah, other factors which we can discuss if someone is interested. But we have to keep this in mind. um, Anyway, also over here I'm not focusing on the particular sources that we study and how this polarization appears in the synchrotron emission, or how what do we infer from this polarization. But if someone is interested, then yeah, of course we can discuss about the details of the polarization that I've shown over here. But since today's talk is mostly on how we procure the polarization data and how do we reach these results, I'll focus on that. Uh, so let's jump into equations and how do we uh, calibrate and all, basically. So let's see this equation. So what we observe are the visibilities, which are basically cross correlations of voltages obtained by two different antennas. Um, so this model visibility is kind of the true visibility which we expect, but we actually observe this observed visibility, which is actually corrupted by many of these terms which we express in terms of Muller matrices. Um, Now, this so let me explain the terms. This B means the band pass, which is basically it takes care of the gain fluctuations with respect to the frequencies. And then there is this complex gain term, which accounts for the atmospheric as well as instrumental gains with respect to time, gain variations with respect to time. And then there is this D term, which is basically the leakage term, instrumental leakage term, which appears mostly in polarization when we are trying to find out polarization in the sources. And then there is this parallactic angle term. So parallactic angle is basically the angle subtended by the source with respect to the like the observer's horizon and the north celestial pole. So as the source moves with time, then this term also appears. But now how we deal with it, we how do we get the correct visibilities, corrected visibilities, is basically to multiply the observed visibilities with the inverse of these matrices in this order, and then we procure the corrected visibilities, and then we do a Fourier transform to get the specific intensity on the like specific intensity of the sources on the plane of the sky. But the thing is, again, this is a little bit simplified version. There are many other terms which we are neglecting for now. Um, and this like this band pass gain over here is mentioned like this, but in principle we take the relative gains, relative band pass gains with respect to a reference antenna, where we consider the phase to be zero at the reference antenna. So ultimately the equation becomes like this, where the cross hand band pass gain term is can be actually refactored into band pass gain, and then something called k cross and chi, which I'll explain later on. And then there is of course this d term and also a p term as well. So sorry, Janki, can you confirm one thing? My cursor is visible, right? Because I'm
Yes,
pointing.
your cursor is visible.
Yeah, yeah. Okay. Thank you for confirming. Yeah. So, continuing on that note, is basically this we have this B term as well as K cross term and chi R term, um, and then D term and P term, which we need to correct for. Now, this K cross, D, and chi are relevant to polarization calibration. So, K cross is basically the cross hand delay, and chi-r is the cross-hand phase, and dr, as I mentioned, is the leakage term. I'll go into like explaining in this individual terms as well, but before that, let me explain you why this cross-hand term is needed to be corrected for polarization calibration. So if we go to the Stokes equations basically, and we try to solve them in circular basis. So first, I'll when you mention that GMRT has basically band 2, band 3, band 4, and band 5 according to the increasing order of their frequencies. Um, Now, band 2, band 3, and band 4 receive the signals in linear they have linear phase and they receive the signals, the linear polarizations from the signals. But then there is a polarizer present which converts this linearly polarized signals into circularly polarized signals. And for band 5, the scenario is a bit different because there is no polarizer and we ultimately get receive the information in linearly polarized manner. But the issue with linear basis, like solving these equations in linear basis, is the linear basis equations are much more complicated and convolved with each other, which if someone is interested, I can again show the equations and all. But the equations become simpler to be solved in circular basis, and that's why people wish to convert all these astronomical signals into circularly polarized form, which are done using a polarizer in this three bands. So in the circularly polarized circular basis, actually the parallel hand, if you see the parallel hand, meaning when we are correlating the R channel with the R channel of the two antennas, so that is called the parallel hand correlations. Whereas if the R channel from one antenna is correlated with the L channel, that is the, you can consider it like the right hand circularly polarized signal is correlated with the left hand circularly polarized signal of the other antenna, then we call it as cross correlations. I mean cross hand correlations. So the parallel hand correlations, if you see in the Stokes domain, it's basically a combination of Stokes I and Stokes V. If you see these two equations, whereas the cross hand like visibilities, they involve Stokes Q and U. Now, if we like Stokes I basically gives the total intensity, whereas this Stokes V gives us information about the circular polarization, whereas the Stokes Q and U, a combination of them, actually gives us the linearly polarized signals, information about the linearly polarized signals. Uh, but these are again kind of like the model visibilities. In principle, these are corrupted by these terms, as I mentioned over here. Now the equations become like this, as I've shown over here. Yeah, these are like kind of elaborate equations, but we need to not, I mean, we don't need to concentrate on this whole equations. But the thing that we need to focus on are the D terms over here. And then there are this row, which is basically the cross hand phase. And then there is psi term, which is the parallactic angle term. Now, these individual leakages are not much important, not much. So these can be easily neglected. But when they come in terms of like the summation of the two leakages and also multiplied with the cross hand phase, the term cannot be neglected anymore. So what happens is in the parallel hand correlation, we can see the equation still remains as I plus V and I minus V. Whereas in the cross hand correlation, there are many more terms, where there are D terms, and then there is a cross hand phase term as well. Now, for our sources, we can actually neglect the Stokes V because we hardly do get circular polarizations. So we can neglect this. But if this also remains, we need to solve for this DRI plus DLJ star, or the minus, or the summation or the difference between the two, and multiplied by the e to the power I phi term. Uh, so if we take the summation of these two visibilities, then what we get is basically this equation, where we can see if we can solve for this D terms, then ultimately like this remains, e to the power I phi term remains as the unknown. Then so it goes on, like we solve for the D terms first, and afterwards we solve for the cross and phases. So this is how we solve for it. But let me go to the flow chart that we kind of follow. uh, after we get the GMRT data. So this involves actually all the everything that we do from the start to the end um, with the data. So I think many people are familiar with GMRT data over here, and we use CASA, Common Astronomical Software Application, to reduce the GMRT data. Um, so GMRT data is available in both formats, either in LTA, which is the long-term archival form, or in FITS format. Uh, they are available in both, but we try to not download the FITS format data because sometimes the FITS format data is corrupted. So we download the LTA format data only, and we perform the list scan and GVFITS task on it to convert it to FITS format, and then we do something called import UBFITs, which I mean we do import GMRT for GMRT because it involves some of the more modules to convert it to a measurement set file. Now, after we get the measurement set file, what we do is to perform flagging on that to remove the bad data that are present in the visibility file. Now, this flagging we do is like clipping of the bad data that. So the flagging involves multiple things like clipping of the bad data which are way above your data, and you can identify like you can give an amplitude cutoff over there. Which you can perform on the data. Also you can you can remove the bad channels, and also the first timestamp of each scan, because it usually it is bad. And also we have seen that the first channel gives a very high value for GMRT, so we also remove that data. And also we run some automated flagging like TF-crop, which performs statistics and removes the outliers. Now, after this initial flagging is done, which where we just remove the obvious bad data, um, then we perform normal calibration. So like, which is not the polarization calibration, the general calibration, where we use Sedzansky to set a model of the flux calibrator, and we say that this should have such amplitude at such frequencies, and based on that it does the calibration. It does solve for the, as I have said, band pass, complex gains, all this. And then we also transfer the solution to the for the phase calibrators, where we know we can set the model that the phase is supposed to be 0 for the phase calibrator, but we don't know the amplitude, so we transfer the solution from the flux calibrators to the phase calibrators. And finally what we do after this is to apply the calibration. Here we can apply it on the only on the calibrators or even on the targets. But after applying the calibration, we can again see some more bad data coming up, which were lying hidden before the calibration was done. Uh, so after those arise, we need to flag them again. And again, by following the methods that I've already mentioned, we also use our flag over here, which is an automated flagger again. Uh, and after those high bad data points are again removed, we perform a clear cal to clear the already applied calibration. Uh, so after this clearing of the calibration, we again follow the same method to calibrate it again. And we do follow this whole process in a cycle till we are satisfied, and till the calibration converges. So we will be getting the same model, same results, same solutions in each rounds. At that point, we know that the calibration has converged, and we stop doing it. So after this comes the, so this is the basic calibration that we need to perform. But after this comes the polarization calibration. And the polarization calibration will involve setting of the polarization model, like we set it for the flux calibrator, now we set it for the polarized calibrator or the unpolarized calibrator, which we are using for polarization calibration right now. And the polarization calibration involves mainly three steps, as I have shown before in the, like I showed that the observed visibility and the corrected visibility, so where these are like gets multiplied or corrupted by these three terms, basically the cross hand delay, the leakage term, and the polarization angle term. So I'll get into the details of these three steps, basically, that how do we solve for this, and what do we do, and what are these also. So I'll explain them in details. Um, so over here I'm stopping till the polarization calibration. I'll get back to it later on, like what other steps we do afterwards. But let's first concentrate on what these three calibrations mean. uh, so first, the cross and delay calibration is required because we usually perform the parallel hand delay calibration while doing bandpass and gain calibrations, and also we do an extra step of parallel hand delay calibration as well for safety purposes. Um, but this cross hand delay is not sorted out over there. Uh, so basically, this cross hand delay means the cross hand phase has a slope with respect to frequency, which is causing this delay. For but this the delay magnitude kind of remains same almost for all the baselines, and these are opposite for the two different cross and correlations. Um, and we solve this. So basically, we ask CASA to solve it for us, and we use the task gain cal with the gain type called K cross, which takes care of this cross hand delay, which measures this cross hand phase slope with frequency and solves for it. And for this, we need to have strong polarized calibrators, which has like some certain values of RLLR, so that we can actually estimate this cross and delay and apply that calibration solution to our observed visibilities, basically. Yeah. And the next one is the leakage calibration, the next step, basically. So I have been talking about leakages, but leakages are basically nothing but basically the leaking of so there are two feeds, right? As I mentioned, that one is receiving left circularly polarized signal, and another is receiving the right hand circularly polarized signal. So there can be leaking of one kind of signal, that is, say for example, the LCP to the RCP, and also vice versa, like the RCP to the LCP. This is because the feeds are not properly made. Sometimes they are not properly orthogonal to each other, so there can be such leakage happening. Um, and due to the leakage, the voltages that we receive are not properly, like ER times e to the power minus I phi. It also involves a leakage term times the other signal as well. Same for the left hand voltage. And what happens is, as I've mentioned before also, these equations, that the parallel hands remain unaffected because these terms are not very highly, like this doesn't have much impact. But when we get the summation of the two multiplied by the cross hand phase, it becomes really important, especially for the polarization results. So we need to calibrate this, we need to correct for this. Now, if we are using polarization calibrator to correct for it, then we can see that there is a parallactic angle term involved with the equation. So we need to actually have, we need to observe the source for a large parallactic angle coverage, say about 60 degrees. that is the source should cover 60 degrees on the sky, on the plane of the sky, because I mean the calibrator source, because then only we will be able to solve for this phi term, the parallactic angle term, and that will give us the proper leakages. Uh, so now this leakage calibration can be done in certain ways, which I'll go to. So we use the task polcal, again ask CASA to solve for it. We give it the models of polarization. Um, we can solve leakages with a polarized calibrator as well as an unpolarized calibrator. Uh, so the polarized calibrator will have some value of Stokes Q and U, since I said this Stokes Q and U represent the state of linear polarization. So if it's a polarized calibrator, then it will have some amount of Stokes Q and U. But if it's an unpolarized calibrator, then it will have QU to be 0. Now we can think of the leakage to be something like something leaking from the Stokes I to Stokes Q and U. Um, which is increasing the value of Stokes Q and U unnecessarily, and will give us wrong information about fractional polarization or the polarization angle. So in order to correct for it, either we provide a source with known QU values, and then we say that the observed value is not this, so we need to correct for this, or we give an unpolarized source where QU is 0, and we say that like this the observed is this much higher than 0, so we correct for that. So that is what leakage calibration actually means. Now it can be done in three ways. Just as I mentioned, it can be done with source with zero polarization, that is an unpolarized calibrator, with the pole model to be QU equal to 0. Then we use the pole type DF. These are some code names that CASA understands and solve for the D terms only. We can also give a source with unknown QU values, um, a polarized source which has certain QU, but we don't know the values. Then for that, we use the pole type DF plus QU, where it solves for both the leakages as well as the QU values. And there is another way where we know the QU and we can set the model for QU, and we ask it to solve for DF plus X, where it solves for D term as well as the position angle. Now, for us, the position angle, I mean, for circular basis, the cross and phase delay, the cross and phase basically reflects the position angle only. So but it's not the case for the linear basis. It only applies in the circular basis. And for these two particular ways, we need to have scans of this calibrator, more than two scans of the calibrator. At least three scans are needed, and more is better. And also we have to keep in mind that we have to have a large parallactic angle coverage, which is about 60 degrees is needed. Now I've taken this particular thing from this synthesis imaging tutorial, and this I find very helpful our for a source of our we kind of refer to this document quite a lot. So after this talk, maybe I'll share this whole presentation so that you can also click on this links and check out all the links that I've given so far, and then there are more to come. But yeah, the next step of calibration is the polarization angle calibration, as I mentioned. um, so in when we are doing normal gain calibration, normal basic phase gain calibration, we set the phase gain at the reference antenna to be 0. So what we do is when we calibrate, we consider the phase gain for a particular antenna to be with respect to the phase gain of the reference antenna. So basically, it's a difference between the phase gains of two antennas, where the basis should be the reference antenna phase gain. Now, if we check the difference between the phase gains of two different antennas which are unrelated to the reference antenna, then of course like if we expand the equation, then it will be like the phase gain of that antenna minus the phase gain of reference antenna minus the phase gain of other antenna plus the phase gain of the reference antenna. Like if you simply put this into this, then that will be the equation. But if we take the parallel hand terms like both RR and both LL for the two different antennas, then what happens is this reference antenna terms gets cancelled, because this will have a minus of the phase gain of reference antenna, and this will again have the plus of phase gain of reference antenna. So this will cancel each other. But when we are taking the difference between the right hand phase gain of one antenna and the left hand phase gain of other antenna, then the issue appears is that these terms do not get cancelled out. So what happens is, and for polarization calibration, we actually set this alpha RF to be the, I mean, the reference antenna phase gain to be the polarization angle of the polarized calibrator. So, say for example, we are using a polarized calibrator which has a position angle of phi. Then this alpha RF will be phi and alpha LRF will be minus phi. And that is how over here we get a difference of 2 phi term, I mean an addition or a difference of 2 phi term in this phase gains, which we need to correct for. And that is what the polarization angle calibration does. It corrects for the 2 phi, where phi is the angle of the given polarized calibrator. Now, it's better that we choose a polarization calibrator with 0 RM. That is, the polarization angle doesn't change with frequencies, so that this stays robust with the change in frequency. And we use the task polcal with pole type XF. Yeah, CASA solves for it. So now I'll quickly mention that when we are observing with GMRT, or like when we want to do a polarization observation, what do we need to do in extra? So one thing which is a must is that we have to opt for full polar observation, which will have all the four correlations like RR, LL, and RL and LR, because RL and LR are the most important for solving the polarization calibration in circular basis. Uh, Now, as usual, we need to have a flux calibrator observation at the beginning and the end of the observation, so that your flux calibration is properly done throughout the observation. And then the phase calibrator and the target needs to be observed in a sandwiching manner, like like the phase calibrator should be observed and then the target and then the phase, like that, like an alternate phase and target source observation needs to be done. This is to um, assure that the phases between the phase calibrator and the target doesn't deviate much and your phases are calibrated properly. Now coming to the leakage, I mean, I mentioned it before as well, that leakage can be solved with polarized calibrator as well as the unpolarized calibrator. So we have two different strategies for the two different ways. So we have to decide before the observation how we want to solve the leakage for this two for the observation for the data. So and we have to observe accordingly. uh, if we are doing the calibration with a polarized calibrator, then we need to maintain a proper parallactic angle coverage. So we need to have multiple short scans of a polarized calibrator with a good parallactic angle coverage. But if we are solving leakage with an unpolarized calibrator, then this is not required. Um, and we can actually observe an unpolarized calibrator, um, like a single scan will do. And a single scan of polarized calibrator is required to solve for the polarization angle. Uh, so this can be done with two single scans, but in order to be safe, because one scan might get corrupted, we always take more than one scans. But if time is limited, like your observation time is not much and we cannot cover multiple short scans of polarized calibrator, then we have to go for this unpolarized calibrator leakage solution method. So, like, coming on to our what we have noticed with our GMRT observations is that 3C286, which is a polarized calibrator, works best for GMRT. And there is also another calibrator 3C138, which is also polarized, which as well works well. There are,
Samoli,
yeah, sure.
can I
Yeah,
interrupt the
yeah,
question?
yeah, sure.
So, how nearby these polarized calibrators has to be compared to the?
Okay, so this doesn't need to be very nearby. Like it can be far away, but yeah, it can be far away. There's no issue with that um, because
Does it depend on which part of the through which part of the galaxy, our galaxy, we are looking
yeah.
at?
uh, So I understood what your question was. Yeah. So basically, it doesn't need to be as close as the phase calibrators. It's not affected by those minute changes in phases. If we shift from the source to that calibrator, it can be far away. Like we are observing far away calibrators only, which are, because there are very few polarized calibrators available, and it doesn't
Can,
affect our results. Uh,
can I have an additional?
yeah.
So, have you tried with using two different polarized calibrators at two different directions and checking that for consistency? Yeah,
Uh,
Preeti is nodding.
mhm.
Yeah. So just to add, I think yes, we've tried that. So Janvi has tried both. Sometimes using just a polarized and unpolarized and everything. They give similar results. So we've tried that.
Yeah, similar leakages.
Yeah.
Yeah,
Okay, thanks.
yeah. So, yeah, but these are not very close to the sources. Uh, yeah. Anyway, as I was saying, that 3C147 and 3C48 are also serve as good unpolarized calibrators. So 3C48 is a polarized calibrator, but at GMRT frequencies, like at such low frequencies, it becomes unpolarized and can serve as a good unpolarized leakage calibrator as well. What we observed with OQ208 is it doesn't work at all with GMRT because the flux density itself is very low. It's a caution. It's better not to use OQ208 in any of the polarization calibration observations as a calibrator. Now, all these things, most of these things are documented in a polarization document by a group, which you can check out from this archive link. And also, there is this VLA polarimetry web page, which includes all the polarization models as well as the different polarization calibrators. But yeah, it's better to use something between all this, which I've mentioned for GMRT. But there are other calibrators which are also present over there, mentioned over there. You can go through what the calibrators are and in which cases they can be used. But those are mainly mentioned for VLA, like in terms of VLA. Uh, but this particular web page also gives us the model for the calibrators, which includes the total intensity of these sources as well as the polarization fraction and the polarization angles at different frequencies. Now, this actually helps us later in our mostly in our calibration, in the way that we need to set a model for calibration, right? So what we do is to extrapolate from these values since GMRT frequencies are mostly not covered with the VLA polarimetry models, we extrapolate the values at our reference frequencies and use that as a model. So mostly the polarization angle, since these are zero RM source, they remain almost similar, but we use some kind of spectral index for the polarization fraction, and extrapolate the values at our respective reference frequencies. Now, going on to the leakages that we get usually for GMRT, uh, it's below 30%. This is from a 2019 data. Things have bettered now, and most of it are below 15% only, as we can see over here. And there are some bad solutions at the edge channels which we need to remove when we are applying this leakage solutions to our data. Uh, so I am this is a leakage calibration from all the antennas and from all the correlations. But I have another plot where I show the leakage calibrations for each antenna, and these are the two correlations in colors. Now there are some high points, as you can see over here, or some low points over here, which we need to remove in order to get a proper leakage solution. Uh, we so if leakage is properly solved, then it will have a pattern like this, but like not exactly like this, but a similar-ish pattern. But if it's completely wrong, if your leakage solutions are completely wrong, then you'll understand that the pattern is completely gone, or it's doing something. Visually it can be identified that the leakage solution has not been properly done. And recently we are using some other schemes also to reduce all this jitterings in the leakage solutions, like introduction of Walsh filters and all. If someone is interested, we can discuss about it later. But without Walsh also, we get proper results. It doesn't affect our science results to a large extent. So yeah. Now, coming back to the flowchart that I was showing, how we go on with the data reduction procedure. So after the completion of the polarization calibration, uh, when we are satisfied with the calibration results, what we do is to apply the calibration on the data, and then we split the target source, and we do a fast Fourier transform on it to image the field, um, and we get the dirty image initially, and we use the model from the same image to calibrate itself, which we call a self calibration. And after a few rounds of self calibration on the Stokes eye image, we get we obtain the Stokes eye image, and also from that finally calibrated measurement set file, we also procure the Stokes QUV images. Now, how does this reflect to the polarization states? So basically the polarization angle, as I've been talking about, is given by half tan inverse U by Q, and the linear polarization intensity is given by root over Q square plus U square, and divided by the total intensity gives us the linear polarization fraction. Whereas the circular polarization is given by Stokes V by I. Now, coming to the final slide of today's presentation, I want to just mention we have a data analysis pipeline where exactly all these steps are followed. As I've mentioned, as I just talked about, all these steps are over here, and the pipeline link is given over here, which is an old pipeline updated by every one of us, and according to the issues that we have faced in the recent GMRT data, we have updated it accordingly, and this is maintained regularly. Whenever we find some bug, we try to correct it, and you can contact me or anyone else from our group to if you face any issue while using this pipeline, in case of reducing polarization sensitive data. I have also given a link to the VLA tutorial, CASA tutorial with the VLA data, which one can refer to while doing a polarization calibration. Um, and I have given some screenshots from the pipeline itself, which showcases all the extra things that we do for polarization calibration. Is basically defining a polynomial for extrapolating, as I mentioned now, that we extrapolate the values of polarization fraction or polarization angle from the model that is available in the VLA polarimetry website. So we extrapolate the values of polarization fraction and polarization angle from there. Um, and after that, we do the we follow the general basic calibration steps. And when it comes to the polarization calibration, we set the model of the polarization calibration with the results we obtained from here, by extrapolating the values. So we set them as a model for the polarization calibrators, and then we follow the three steps. Three calibration steps. That is the cross-hand delay calibration step, and the leakage calibration step, and the polarization angle calibration step. And finally, after this, we um, apply this calibration and image it to get such beautiful images of the region with all those polarization vectors. Like we plot the polarization vectors afterwards according to the functions that I have shown, like the polarization fraction value will be root over q square plus u square by I, and the angle will be 0.5 tan inverse u by q. So we plot those vectors accordingly to get the maps of the polarization that we have showed before. Yeah, so that is all I wanted to cover today. Uh, so if there's any question, maybe I can go back to Zoom. Sorry, the Google Meet.
Thanks, Shalmoli.
Yeah.
We have time for questions. So, does anyone have questions? You can just unmute yourself and ask.
Only this the leakage terms that you showed.
Yeah. Mm-hmm.
So this has all those ripples, right?
Mm-hmm.
Any idea why these ripples come? Because I have also seen these earlier. And
The ripples, by that you mean, okay, I have stopped sharing, right? Just a second. Mhm. Sure. So I think now you can see my screen again, right? Yeah. So by the ripples, you mean the small scale ripples?
yes, yes, there are at different scales, right? Different
Yeah.
frequency ranges.
Yeah. So yes, exactly. So this are some instrumental effects, right? The leakage comes from instrument. These are instrumental leakages, and there can be small scale fluctuations with respect to the frequencies, which are obviously giving rise to the small scale things. So something is happening at the small scales also, which is completely instrumental thing, and yeah.
And the self-cal procedure is you mentioned is it's only Stokes I, right?
We do
So,
it currently on the Stokes I only because it's difficult to assign a model for the Stokes Q just by seeing the Stokes Q images, Q or U images. So we do it on the Stokes I, and then finally we obtain the measurement set, which is calibrated, and then we go for the Fourier transform again to obtain the,
yeah, thanks.
yeah.
So there's a question in the chat. Um, what is the flagging procedure used in the pipeline? Is flagging done during self-cal on residual data?
So we do flagging on the residual data. So flagging we mostly do by clipping, and also we sometimes do some manual mode flagging where we get to flag some very odd behaving antenna or some dead antenna. We do all those manual modes of flagging, and we do clipping of the higher points. We remove the bad channels and the observation the scale, the first timestamp of the observation for each scan, that is also removed. And we also use automated flagging like the TF crop and R flag. And R flag we do it on the residual data if it's a calibrator, because that will have a model, but we cannot do it on the target source because we don't have the model. So doing it on the residual data actually helps because there we know for sure that this can be removed.
Does it answer the question, Abhinav?
Yeah. So any details you need, you'll get in that pipeline also. Like all the steps are kind of clearly mentioned, which flagging are done and which is to be done when. So those are also mentioned. So you want to check it out.
Are there any other questions? Okay, so let's thank Shalmali and Preeti today for this great explanation and presentation. And we'll meet again in a couple of weeks.